Have you ever just stopped and wondered why table salt forms those perfect tiny hard crystals? Or why copper wire conducts electricity but the water we drink behaves entirely differently? Well, it all comes down to the hidden rules of chemical bonding. Today, we're diving into this explainer to unpack exactly how atoms connect, share, and sometimes completely steal from each other to literally build the universe as we know it. Let's get into it.
Here's our roadmap. We'll start with the quest for stability, move into ionic and metallic bonds, then look at covalent bonds and sharing. After that, we'll map out molecular shapes and polarity, and finally, wrap up with the magic of water.
Section 1. The quest for stability. So we really have to ask ourselves a fundamental question right off the bat. Why isn't everything just a disconnected, chaotic soup of single atoms? Why does anything form solid objects, liquids or gases in the first place? Well, the truth is, atoms are incredibly needy. On their own, they're inherently unstable, and they kind of hate being alone. Chemical bonding is their clever, perfectly natural solution to that problem, driven by the positively charged nucleus of one atom strongly attracting the electrons of another.
And this brings us to the absolutely crucial octet rule. This is the ultimate goal for almost every atom out there. They are constantly striving to get exactly 8 electrons in their outermost shell. That's how they achieve a stable electronic configuration. It's the main engine driving them to combine. Now, I should mention, hydrogen is a notable little exception here. It only needs 2 electrons to be perfectly happy and stable. But for the vast majority, 8 is the magic number. Now think of bonding as a microscopic tug-of-war. Electronegativity is basically an atom's raw strength in that game. It's their ability to pull shared electrons toward themselves. And fluorine? Fluorine is the undisputed heavyweight bully of the periodic table with the absolute highest pulling power. The difference in this pulling strength between 2 interacting atoms actually determines exactly what kind of bond they're going to form to reach that magic octet.
Section 2. Ionic and metallic bonds.
In an ionic bond, that tug-of-war we just talked about is completely one-sided. This usually happens between a metal and a nonmetal. Take sodium and chlorine, for example. One atom is so much stronger that it just completely transfers, or, let's be real, steals an electron from the other. The atom that loses the electron becomes a positive ion, called a cation. The one that gains the electron becomes a negative ion, called an anion. And because opposites attract, these massive networks of positive and negative charges stick tightly together. This forms hard, crystalline structures like table salt. These things have incredibly high melting and boiling points, and interestingly enough, they only conduct electricity when they're molten or dissolved in water, not when they're solid. If you're mapping this out, chemists capture this absolute transfer of power using simple dot structures. It's a highly logical process. You draw the metal completely empty since it lost its outer electrons, and the nonmetal completely full. Then you wrap them in brackets with their new positive and negative charges on the outside. It's essentially a perfect visual ledger of the electron theft. But when metal atoms bond with other metal atoms, they use a completely different strategy. Neither side wants to hold onto their outer electrons too tightly, so instead of transferring them, they just let them loose. This creates what chemists actually call a communal sea of mobile electrons washing over positive metal ions. This loose flowing structure is precisely why metals like copper, iron, and aluminum have the properties they do. It's why they're shiny, malleable, ductile, and why those microscopic seas allow heat and electricity to flow right through them so beautifully to power our homes.
Section 3. Covalent bonds in sharing.
Okay, so what happens when 2 nonmetals meet? Well, the tug-of-war is much more evenly matched, so instead of stealing, they have to deliberately compromise. We call this covalent bonding. They hit their stable octet by physically sharing pairs of electrons. Sometimes they share 1 pair for a single bond, 2 pairs for a double bond like an oxygen gas, or even 3 pairs for a triple bond like a nitrogen. Because they form these distinct separate molecules rather than massive crystal grids, covalent compounds generally end up as soft solids, liquids, or gases. They have much lower melting and boiling points, and they're usually pretty poor conductors of electricity.
Drawing out these shared connections is basically like solving a tiny geometric puzzle. The least greedy atom sits right in the center, acting as a structural anchor. Then, single bonds connect the surrounding atoms, and the remaining valence electrons are just dealt out like playing cards until every single atom reaches its perfectly stable octet. It's a really satisfying balancing act.
But here's the nuance, and this is super important. Just because atoms are sharing doesn't mean they share equally. If 2 identical atoms bond, like 2 hydrogens, their electronegativity is exactly the same. The difference is 0.
So they share the electrons perfectly equally. That's a nonpolar covalent bond. But if you have two different atoms, like hydrogen and chlorine, one is going to pull a little bit harder. The electrons spend more time hanging out near the stronger atom. We call this unequal sharing a polar covalent bond. And the bigger the difference in their pulling strength, the more polar the bond becomes.
Section 4. Molecular shapes and polarity.
Because all electrons are all negatively charged, they naturally absolutely hate being near each other. They actively repel one another. This gives us VSEPR theory, valence shell electron pair repulsion. Now it sounds super complicated, but all it really means is that electron pairs physically push apart from each other as far as mathematically possible in 3D space to minimize that repulsion. And crucially, unshared lone pairs of electrons active and bulkier, repelling way more strongly than electrons that are safely locked up in a bond.
So this microscopic repulsion creates a strict taxonomy of geometric shapes. If an atom has bonds pushing exactly opposite to each other, like in carbon dioxide, you get a straight 180-degree linear shape. But look at water, H2O. The oxygen atom has two bulky lone pairs of unshared electrons. They physically push down hard on the hydrogen bonds, forcing the molecule into a distinct bent shape. If you have one lone pair pushing down, you might get a trigonal pyramidal shape, like ammonia. And if you have four equal bonds pushing away in all directions, you get a tetrahedral shape, just like methane.
That physical geometry, combined with the bond polarity we just talked about, determines the molecule's overall identity. If a molecule has a perfectly symmetrical shape, like methane, the internal pulling of electrons cancels out in every direction. It becomes completely nonpolar. But if a molecule is asymmetrical, like the bent shape of water we just mentioned, the charges don't cancel out. You end up with an unequal charge distribution, leaving one side slightly positive and the other slightly negative. It becomes a polar molecule, acting almost like a tiny little magnet. And as we'll see next, that tiny magnetism literally changes the entire planet.
Section 5. The magic of water. See, molecules don't just exist in isolation. They interact with each other through intermolecular forces. Nonpolar molecules are held together by very weak forces called van der Waals forces. But water relies on something way stronger, hydrogen bonding. This is a superpowered attraction that only happens under very specific conditions, when a hydrogen atom is directly bonded to a highly electronegative nitrogen, oxygen, or fluorine atom. Because water is H2O, it forms these incredibly strong hydrogen bonds with neighboring water molecules.
Because water is bent, it's highly polar. And because of those powerful hydrogen bonds, water molecules stick together tenaciously. This microscopic stickiness is exactly why water boils at such an unusually high temperature compared to similar molecules. It's why trees can pull water all the way up to their highest leaves, why it acts as the perfect solvent for life, and frankly, why belly flopping into a pool hurts so much. It is entirely dependent on its atomic geometry. Bringing it all together into a summary matrix, we can see how entirely different realities emerge from just three simple electron strategies. Ionic bonds transfer electrons to build rigid, high-melting crystals. Covalent bonds deliberately share electrons to form flexible molecules. And metallic bonds create a communal sea that brings us conductive power grids. Everything scales up perfectly right from the electron. It is genuinely fascinating to realize that our entire macroscopic reality, from the salt on your fries to the copper wires in your walls to the water in your glass, is dictated by these tiny atomic rules, driven by an atom's simple desire for 8 electrons. Next time you take a sip from a glass of water, ask yourself, what invisible microscopic forces are holding it together right now? And just how many unseen chemical forces do you interact with every single day without even knowing it? Thanks for exploring the building blocks of our world with me in this explainer. Keep wondering and keep learning.